Well, this is the second to the last video covering, I guess, reactions of organic compounds. I started with this page just to sort of show review of where we've been through organic chemistry. First semester, we've looked at, I guess, as far as reactions, we've looked at alkyl halides, and we said that the alkyl halide can be attacked by nucleophiles either at the carbon connected to the halogen or at the carbon next to that carbon, so the beta position. We talked about E2 and E1 and SN2 and SN1. And then we jumped over as our second discussion on polar reactions. We looked at alkenes and how alkenes were always the nucleophile in polar reactions attacking electrophiles. And we saw that alkynes could do the same, but they had a unique reaction where alkynes could be attacked by a strong base. The alkyne with a hydrogen off the triple bond could be attacked by strong bases. That was a unique reaction. One that alkenes and alkanes, which are both nonpolar, but alkenes being a little bit more reactive, at least could react with electrophiles, but they could not, and they cannot react with strong bases to form new organic molecules. So only the alkyne was able to go the other way and be attacked by some sort of nucleophile as a strong base. Typically, both the alkenes and alkynes, again, in polar reactions, were attacking electrophiles. And then in the last sort of quadrant here, dienes. We've looked at the reaction of dienes with electrophiles and how it's so important to pick the right carbocation. If this is an asymmetric diene, wherein we have some group on the left side that does not show up on the right, and this becomes a pi bond that's different from this pi bond, meaning again an asymmetric diene. We had to pick who gets to attach to the electrophile. Pi electrons B attaching it here, or pi electrons A attaching it to this position. We always had to leave the positive charge next to the double bond, so we always had to put the electrophile on the pi electron such that the positive charge is allylic or resonance stabilized, but we didn't know which, and it was best to draw. And once you know which one's most stable, go through that carbocation to the final product. Where we are now is dealing with a reaction of dienes that does not really fit underneath just the umbrella of draw an arrow between something negative and something positive. It really doesn't work here. We have to go into orbital theory. So this is going to be the first of two videos discussing the Diels-Alder reaction involving a diene. But we're going to have to do, as we look at the Diels-Alder reaction, there's my big eye, we have to go into what's called molecular orbital theory. Molecular orbital theory, which just builds on atomic orbital theory. So let's go there. Now hang on to your hats. I know it's not fun going into quantum mechanics. It's like it's a world of fuzziness. So we know, like, if we were to take just a simple alkene represented by, I guess, a Lewis structure that looks like such, where we have two carbons, 4 hydrogens, and a double bond between the carbons. Now we know if this was representing that structure, these two carbons in black, these being the hydrogens, and we were looking at this as it's drawn, where the hydrogens and the carbons are in the plane of the paper. So these carbons here, we show, as best we can, a pi bond between these two. Well, with this, they're showing it using these white bonds and sort of illustrating that the pi electron density is above the carbon and below the pi electron density. And these kits are just little kits. They aren't, I mean, just like quantum mechanics helps us understand a little bit of what's going on at the molecular level. It's not perfect. It's just a tool that agrees with data, but it's just, again, a picture that's created that may not fit the reality. But in this bond, we don't have the representation of what would be the sigma bond between the carbons, head-to-head overlap. But this little kit does a pretty good job of sort of showing some features of a double bond that you can't rotate. I can't rotate these carbons round and round. It's locked in by the pi bonding. But I want to go ahead and jump to a picture that you may remember from the very beginning of our discussion on orbital theory and what a pi bond is. We said it's a side-to-side overlap. So it's kind of like this, a side-to-side where we have a p orbital here and a p orbital here that overlaps both on the top and the bottom. So side-to-side overlap, of two p orbitals. So these are our carbons, and we're going to now just take this structure that we were looking at from the top and turn it to the side. So that's what I see here. Two p orbitals, one for this carbon and one for this carbon, overlapping side by side. Now, what's with the colors? Colors are very important as we get into molecular orbital theory, which we have to do to understand Diels-Alder reactions. We could say, look, there's two sides of a p orbital according to quantum mechanics. The wave nature, crest-trough nature of a orbital has to be captured. Waves look like this. Trough and crest. If we had our little boat on the water, the crest would reflect the distance from the center of the earth to the boat, and the trough would be, of course, closer to the center of the earth. But these red and blues that we have in quantum mechanics physically don't represent anything other than just the wave nature of the electron in that p orbital. So you have to be careful. It doesn't mean more energy on the red and less energy on the blue. It's just capturing the wave nature, and the plus minus is just capturing the crest trough nature of a wave. We do know this, that if we take two waves, quantum mechanically, orbitals, and we start having them interact, pushing them close enough together that the frontiers, because we know these aren't hard shells, we know these just capture 90% probability of finding the electron. So these are waves. They don't end. Waves don't end and all of a sudden just drop off to zero out there in the ocean, nor they do it in the quantum mechanical world. So these waves start to interact. And we can have what is called constructive interference, where crest meets crest, and the crest gets bigger, and trough meets trough, and the trough gets deeper. So these are constructive interactions as we line it up here, and that would give us a lower energy new single orbital for electrons. We'll just show them as our spin up, spin down, to occupy. So we could consider the orbitals separate from the electrons that are in these orbitals. We talk that way, these orbitals that electrons sit in. We can have the consideration of their overlaps and then consider how they are filled up. So we can say orbitals could overlap constructively, giving us a lower energy, what will be a bonding MO if we put electrons in. And we can also, and this is the weird thing about quantum mechanics, you can't have it your way of lowest energy only. It's weird, but if they can overlap constructively by the same degree, they can overlap by the same degree, they can overlap destructively. So it's always 2 in, 2 out. 2 p orbitals, 2 new pi molecular orbitals. One made through constructive, but if we can have constructive, I hope you're going to respond to this. If we can have constructive, we must have with that destructive. Constructive, when you even say the word for quantum mechanics and it hears, oh, I can constructively overlap, it's also saying I'm destructively overlapping also. That's weird stuff. We don't say it's sometimes constructive and sometimes destructive. No, it's both. Weird stuff. So this can constructively overlap, and by the same token, it can destructively overlap. So we can have crest, or what do we say, crest to trough and trough to crest. And that would give us, if those waves hit, a nodal plane where the waves cancel each other out. And what that means is the probability of finding the electrons in that space where they cancel out is 0. So these orbitals then don't have a bonding nature where they bring the orbitals, the orbitals come together with a greater expression in that space like we have here. If we had +5 on this edge and +5 on this edge, when those edges overlapped, you would get 10. And we can square that value, and the probability of finding the electron would be very high right in this overlapping region, which would hold, which would make sense, the two nuclei together. So there'd be a bonding MO. Of course, if that value is 0, then there are no electrons. These nuclei, again, the positive carbon nuclei are right here, it would fly apart. Right, so that's a long development of a molecular orbital diagram or description here on the right for a single pi bond. We can use this MO description here on the right for anything from an alkene where there's a pi bond between carbons, just like we've talked about, or we can even consider for a carbon-oxygen double bond, pi bond. Now it's changes a little bit because oxygen's a different element than carbon, but it has the same basic nature of two p orbitals. I'm going to draw little balls. These are coming right out towards you. Two p orbitals that overlap constructively and thus destructively. Now oxygen, since this was oxygen, more electronegative, the bonding MO is going to actually cheat towards the oxygen. We'll have more expression of the bonding MO towards the oxygen. But guess what? In the same degree, the antibonding orbital has more expression on the carbons. Good stuff, this quantum mechanics. All right, let's jump to a new structure and be done with this little short video on molecular orbital theory. So I'm building here my butadiene. My but because we have 4 carbons, and my diene because I have 2 enes, one here and one here, and they're conjugated, not alternating double, single, double. More importantly, we have overlap. If I were to kind of try to illustrate the p orbitals, they're coming straight out towards you as we look at this butadiene. Let's flip that over, sorry. We have a carbon here that has a p orbital coming straight out. Carbon here that has a p orbital coming straight out. Carbon here, p orbital straight out, and such in the last one. So we can kind of see let's just turn this over. We can kind of see that, oh, I would have p orbitals here, 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 and here overlapping. We show the pi bond as between just these 2 carbons from outer carbons to inner carbons, and no pi bond in this gap. But as we kind of start to think about the p orbitals and how they're here, it doesn't make much sense why there couldn't be some pi bonding, since we have a p orbital here and a p orbital here, just about as close to each other as they are between these 2 carbons. They are between. You can't shut it off. There would be some expressions of the wave. What do they do here in this gap? Well, to capture that, we draw a pi molecular orbital, pi MO description. And in order to do that, we just start saying what we're going to consider for just pi molecular orbital descriptions are p orbitals. So I'm going to represent these p orbitals just with my horizontal line, saying I have some orbitals to fill. I'm not going to worry so much right now about the electrons in red. I'm just going to say if I had 4 atomic p orbitals, like I do for butadiene, on these 4 different carbons, each having its own p orbital, they could yoke or overlap. How do I capture that overlap such that I do include this 2 to 3, carbon 2 to 3 interaction of p orbitals? How do I capture that? Well, we can have all p orbitals constructively overlapping, all constructive, all constructive. Crest, 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 crest. There's my p orbital here. Crest, 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 crest. That butadiene. We could say all the reds sides of the p orbital are on one side, all the blue sides. And I say, well, I'm laughing because there's no red and blue, of course. And you don't know who's crest or who's trough. But just having that lined up such that they can be all constructive. Now you remember what we said, if it could be all constructive, it could be all destructive. So this is the anti-bonding MO for this one, where instead of having constructive interactions in these gaps, there's 3 gaps here, we could have all destructive interactions in those gaps. So these are somewhat related here. This is as good as, it was the best of times, it was the worst of times. And you have to consider them both at the same time. They may not be occupied by your electrons, but we still consider this as present, as real, as something you could excite electrons to. Now our last one. Our last two, sorry. We can have our first destructive interaction right in the middle. There's reasons I'm not going to get into as to why you pick right in the middle. What we can leave, at least just a basic understanding, is we can leave 2 constructive interactions behind on either side. So that's kind of what we see here, a pi bond between the C4, C3, and then C3, C2. There's a nodal plane, so that's going to represent it here. And then we'd have the pi bond on the right, C2, C1, these 2 carbons having a pi bond. So this would be the second most stable MO, bonding MO. And then we can have, so as we're going here, the nodes, 1 node, we can have 2 nodes where we place the nodal planes not here and here, but symmetric. So there's some symmetry here for our 1 node. We can have destructive interferences go up from 1 destructive to 2 destructives and leave the pi bond in the middle. Now that is not seen here. Well, the reason why we don't worry about this when we don't show some pi bonding here, like we would see here, is because we only have 4 electrons. So as we finish this out, we have a no node, 1 node, 2 nodes, where we change the destructive interference such that we had 2. We'd have crest to trough and crest to trough from the outsides in, and we had a crest to crest, trough to trough interaction between these 2 carbons. And that's a valid molecular orbital. But it's just not occupied. So let's take those electrons and finish this off. Those electrons, we only had 4. 2 pi electrons. 1, 2, 3, 4. So 4 red arrows. So we fill up, according to Aufbauer principle, still the same principle, the lowest energy orbitals, the fully constructive, and then the second orbital, bonding orbital, 1 node, we fill in the other 2 electrons. Now if we look at where these electrons are then, according to these orbitals, we can sort of understand that there is some pi bonding in this gap. How do we see that? Which of these orbitals reveals a little bit of pi bonding in this gap? So this one here, this one here. I hope you're saying this one here because you can see, oh, they're showing some constructive overlap between C2, C3, and there's 2 electrons. So there is some pi bonding, not revealed by skeletal structures, but revealed by pi MO descriptions. Do you see the point? That these drawings may not really tell the whole story. There is some pi bonding in this gap according to this lowest energy molecular orbital. Now let's finish. There is certainly more pi bonding here because not only do we stretch it amongst 4 carbons all the way through with 2 electrons, that means those 2 electrons can be found in any of these gaps, here, here, and here. But there's a little bit more pi bonding between C1, C2, C3, C4 because of these 2 electrons, which are expressed more between C1, C2, and C3, C4, but not in this gap. So there's more electron density on the edges than there is in this middle gap. That's because of our pi MO description. Now I do want to just say we could have had the same pi MO description for the S trans and the S cis. So the S trans, we have this conformation, but we can also have what's called the S cis, meaning these 2 double bonds conjugated to each other can be across from each other, that's S cis, or as it's drawn here, we can have it in the S trans. Alright, that's it. We can do a lot now with this view of red and blue. We can say, hey, these are MO descriptions down here. Lowest energy MO descriptions, lowest energy MO descriptions for pi bonds within a non-conjugated diene where we have two basically alkenes that can't communicate with each other. There's no yoking. This is sp3. It cuts them off. But we can go to conjugated dienes, just like we saw, and we can say, oh, I can consider those 4 p orbitals yoking together, even in this gap here, where there's, in this skeletal drawing, there is no pi bond shown here, but that's really not true. We know if it was crest to crest all the way through and trough to trough all the way through with no node, we get some pi bonding in that gap. There are 2 electrons that can be found anywhere from here to here with no break. And on the bottom, that's those same 2 electrons. Well, that's it. That's my brief discussion of molecular orbital theory. We'll need this as we go into discussion of Diels-Alder reactions. Bye-bye.